A binary tree is a collection of nodes where each node has at most two children called left and right. Traversal means visiting every node exactly once in a systematic way. Preorder root left-right. Visit the current node first, then recursively traverse the left subtree, then the right subtree. Inorder left root right. First traverse the left subtree, then visit the node, then the right subtree. Postorder left-right root, left subtree, then the node. Analogy, you pick up a book on a shelf, the root, before exploring the shelves on the left side and then the right side. In a binary search tree, this visits keys from smallest to largest. Analogy, you clean a room only after you have cleaned everything inside it. Properties. Every node appears exactly once in each traversal. The three orders are permutations of the same set of nodes. Knowing two of them with an order uniquely identifies the tree. The depth-first nature means the order depends only on the relative positions of nodes, not on external data. Simple example. Consider the tree. Are at the top B as left child of A, C as right child of A, D as left child of B, and E as right child of B. Preorder traversal gives A, B, D, E, C. Inorder traversal gives D, B, E, A, C. Postorder traversal gives D, E, B, C, A. Recursive pseudocode. Preorder function, if node equals null return. Visit node, recurse preorder on node left, recurse preorder on node right. Inorder function, if node equals null return. Recurse inorder on node left, visit node, recurse inorder on node right. Postorder function, if node equals null return. Recurse postorder on node left, recurse postorder on node right, visit node. Complexity analysis. Time, each call touches a node once and does big O of 1 work, so T of n equals theta of n where n is the number of nodes. Space, the recursion stack holds at most the height h of the tree. In the worst case, a completely skewed tree h equals n, big O of n space. For a balanced tree h equals theta of log n, big O of log n space. Mathematically, the space S of n equals h equals the maximum of depth of left and depth of right plus 1. The algorithm is optimal because any traversal must at least read every node. Iterative traversal with an explicit stack. When recursion is not allowed, for example limited call stack size or language without recursion, we simulate the call stack with a manual stack data structure. Preorder stack. Preorder iter root if root equals null return stack equals new stack dot push root, while not stack dot is empty node equals stack dot pop visit node. If node dot right not equals null stack dot push node dot right first if node dot left not equals null stack dot push node dot left on top. Inorder stack. Inorder iter root stack equals new stack cur equals root, while cur not equals null or not stack dot is empty. While cur not equals null stack dot push cur equals cur dot left end, while cur equals stack dot pop visit cur equals cur dot right. Postorder 2 stack or 1 stack with visited flag. Postorder iter root if root equals null return stack equals new stack last visited equals null cur equals root while not stack dot is empty, or cur not equals null if cur not equals null stack dot push cur equals cur dot left else peak node equals stack dot peak if peak node dot right not equals null, and last visited not equals peak node dot right cur equals peak node dot right else visit peak node last visited equals stack dot pop. Complexity comparison. Time same theta of n because each node is pushed and popped a constant number of times. Space, the explicit stack also stores at most h nodes, O of h space, identical to recursive version. The constant factors differ. For example, 2 stack postorder uses 2 times h. Thus, iterative and recursive versions are asymptotically equivalent. The choice depends on environment constraints. Inorder traversal of a binary search tree BST. A binary search tree obeys the invariant for any node. X, every key in X left is smaller than X key, and every key in X right is larger. When we perform an inorder walk left root right, we first visit all smaller keys left subtree, then the current key, then all larger keys right subtree. By induction on the height of the tree, we can prove that the output sequence is strictly increasing. Proof sketch. Base case, a leaf node yields a 1-element list, which is trivially sort. Inductive step, assume inorder left yields sorted list L. And Inorder right yields sorted list R because all elements of L less than node key less than all elements of R concatenating L plus node key plus R is sorted. Practical use to obtain a sorted array from a binary search tree that stores, for example, student IDs we call Inorder root, and collect the visited keys. The resulting array can be fed to binary search again or printed directly. Example: binary search tree built from keys 40 20 60 10, 30 50 70 yields Inorder output 10 20 30 40 50 60 70, a perfectly sorted list. A single traversal does not uniquely identify a binary tree, but the combination of preorder plus inorder or postorder plus inorder does, because inorder tells us how many nodes belong to the left and right subtrees. From preorder and inorders. 1. The first element of preorder is the root R. 2. Find R in the inorder list. Everything left of R belongs to the left subtree, everything right belongs to the right subtree. 3. The number of nodes in the left subtree L equals index of R in inorder, tells us how many subsequent elements in preorder belong to that left subtree. 4. Recursively apply the same steps to the left part and right part. Sample calculation. Preorder a BDECF. Inorder DBIAFC. Step 1 root equals a first of preorder. Step 2 in Inorder A is at position 3, 0 base left Inorder DBE right, Inorder FC. Step 3 left subtree size equals 3 take next 3 elements of preorder BDE, as preorder left remaining CF as preorder right. Recurse left preorder BDE Inorder DBE root equals B left Inorder D right, Inorder E left preorder D right, preorder E leaves are D and E. Recurse right preorder CF, Inorder FC root equals C left, Inorder F left preorder F right, Inorder empty right subtree null. Resulting tree matches the original. From postorder and inorders. 1. The last element of postorder is the root R. 2. Locate R in inorder left part equals left subtree right part equals right subtree. 3. Size of left subtree L tells us how many elements at the start of postorder belong to the left subtree. 4. Recursively rebuild. Sample calculation. Postorder DEBFCA. Inorder DBIAFC. Root equals a last of postorder inorder split left DBE right FC left. Size equals 3 left postorder first 3 elements DEB right postorder next 2 elements FC. Recurse left postorder DEB inorder DBE root equals B left postorder D right postorder E etc. The constructed tree is identical to the one built from preorder and inorder. These algorithms run in theta of n time if we store the inorder indices in a hash map for O1 lookups. An expression tree is a binary tree where internal nodes are operators such as plus or times and leaves are operands variables or constants. Traversing the tree in different orders yields the 3 classic notations used in calculators and compilers. A plus b times c minus d. The tree has a multiplication node at the root, with a plus node on the left and a minus node on the right. The plus node contains A and B, and the minus node contains C and D. Preorder root left right yields the prefix notation star plus a B minus CD. Inorder left root right yields the infix notation a plus B times C minus D, normally with parentheses to preserve grouping a plus B times C minus D. Postorder left right root yields the postfix notation a B plus CD minus times. Conversion algorithms. To convert infix to postfix, perform an inorder traversal while using a stack for operators, the classic shunting yard algorithm. To convert postfix to a tree, scan the postfix tokens left to right, push operands onto a stack, and when an operator appears, pop its right and left children, build a new node and push it back onto the stack. These conversions are useful in compilers because postfix, also called reverse Polish notation, can be evaluated in a single left to right pass with a stack and does not require parentheses. Evaluation example using the postfix a B plus CD minus times. Step 1 push a push B encounter plus pop B and a compute a plus B push the result. Step 2 push C push D encounter minus compute C minus D push the result. Step 3 encounter times pop the 2 previous results multiply them. The final result is a plus B times C minus D, which is open parenthesis a plus b close parenthesis times open parenthesis c minus d close parenthesis. Compute traversal outputs. Given a labeled tree, write the preorder, inorder, and postorder sequences. Example, tree with root 1, left child 2, left leaf 4, right leaf 5, right child 3, preorder 1 2 4 5 3, inorder 4 2 5 1 3, postorder 4 5 2 3 1. Rebuild a tree from 2 traversals. Provide preorder A B D E C and inorder D B E A C. Ask to draw the tree. Students apply the reconstruction steps described earlier. Count nodes without building the tree. If inorder and preorder are given, the number of leaf nodes equals the count of positions where a node's index in preorder is consecutive with its parent's index in inorder, etc. Verify BST property using inorder. Given a binary tree, perform inorder traversal and check if the resulting list is strictly increasing. If yes, it is a BST. Expression tree evaluation. Provide a postfix expression 3 4 5 times plus 6 minus and ask for its infix form and the final numeric result. Students convert using a stack, then optionally evaluate. Complexity analysis questions. Compare recursive versus iterative inorder traversal for a skewed tree of size n expected answer. Both big theta of n time, recursion uses big O of n stack space, while iterative also uses big O of n explicit stack. These problems test understanding of the order of visitation, the relationship between traversals, and practical algorithmic skills. Explanation, summary comparison table. Columns, traversal, visitation order, root, left, right, typical use case, recursion space, iterative space, remarks. Preorder, root to left to right. Typical use cases, serialize or deserialize trees, copy a tree prefix expression. Recursion space, big O of H, iterative space, big O of H, stack holds at most H nodes. Remarks, root is processed before children, useful for creating a new tree from a list. Inorder, left to root to right. Typical use cases, output sorted keys of a binary search tree, infix expression with parentheses. Recursion space, big O of H, iterative space, big O of H, two-phase loop. Remarks, give sorted order only for binary search trees. Postorder, left to right to root. Typical use cases, delete a tree, free memory, postfix expression, evaluate an expression tree. Recursion space, big O of H, iterative space, big O of H needs visited flag or 2 stacks. Remarks, children are processed before their parent, good for cleanup. H denotes the height of the tree, less than or equal to n in a balanced tree, H equals theta of log n. In a completely skewed tree, H equals theta of n. All 3 traversals run in theta of n time because each node is visited once. The table helps pick the right traversal for a given problem, and reminds that iterative versions replace the call stack with an explicit data structure without changing asymptotic costs.